So, I will speak in English, sorry about that. So, but tell me if it will be too fast, too slow, then I will adjust, because I don't know how to talk. I have two presentations, and actually two topics. So, and first of all, special thanks for Jost for giving me a chance to talk, because we talked and he said, yeah, why don't you come and talk about this subject? So, the first topic is a story about scientific research, but I'm sure some of you might know that, so then we can go fast with that. So this is the research story, and I presented this story at my job, at my work. And I made it very simple for the people far from science to understand. So, you might find it easy, but maybe it will be interesting for some of them. I found this very nice story, inspiring story, and when I did a presentation at my job, it was 15 minutes, and I got idea that it can inspire the people in their job not related to astronomy. And then the second part is a trip to La Palma Island. This trip I did this year in May, and this is Jost suggested to share some pictures, to share how it was it good or not good, etc. So how was the trip? But I will start with the two slides to introduce myself, because, yeah, I think it's important. So one is, it's a standard presentation I used before, but I'm just using this now as well. So, this is the professional slide, my professional career, but the second one will be the astronomy related. So, after I graduated, originally my career started in Moscow, Russia. This is where I'm from. And after university, I worked as a project manager. Then I joined a joint venture in Shell. Also worked as a project manager. Then I worked in the computing center, service lead. It's all about IT and about the providing IT services for the different countries in the regional role. I moved to Belgium to work in the other company, which is called IPCAS in Leuven. So I live in Leuven. Then I worked as a project manager for IoT. And finally, earlier this year, I joined Umicore in Brussels as a data engineer. So this is a little bit of snapshot of my career, and also explaining why I'm in Belgium. So, and that was related that Shell is in oil and gas. So my career is not related to astronomy; it's related more to IT, oil and gas, and then I worked in IPCAS, which is also oil and gas related. Okay, so the second topic is that same timeline, but more like high level about astronomy specific. So my first astronomy touch was at school when I got my first astronomy book from my father. I was very interested. Then my parents presented me my first telescope, and I also as a child participated in astronomy Olympiads. So you know, this is the competition between the schools when you solve tasks. And I decided to continue my education in university, and I graduated as astronomer. And that was in Moscow State University, astronomy education. But I decided not to continue astronomy as a professional, doing the PhD. I decided to work in the industry and not in the scientific research. So that's why this professional career started, that you saw in the previous slide. Now, astronomy mainly was armchair astronomy with the books, but recently I purchased the Dobson ultralight travel telescope, and now I'm re-exploring this from the observational point of view. I must say that the relocation to Belgium helped to start the astronomy again, because in Moscow it's impossible to do the observations because of the light pollution and all other reasons. And in Leuven, when I lived, it's also the environment helped back in the days to start the astronomy journey again, which I was doing in my childhood, because I did a lot of observations with my first telescopes in my channel. Am I explaining it right, clear? Okay,
Yeah.
good.
I've
So-
got one question. Why did you decide to stop as an astronomer to go to the other job?
So, there were a couple of reasons for that. The first reason is that I was interested in IT and computers also. So, both astronomy and IT computers. And IT computers, and I wished to start a job early. So, it was, let's say, an easy start to, as a freelancer, to do some IT job in the university and then to continue professionally. And the second reason is that the money at that point, well, it's still now actually, but at that point it was in Moscow, Russia, so in order to get enough money for kind of okay living, in astronomy you need to spend a lot of years until you reach certain level. While in the IT industry it was booming, so it was very easy to get more money actually. So there was a financial reason, because as an astronomer it was difficult to make a family, child, etc. in a good financial. So, and I was already married at that time, and then I said, okay, maybe for the family reasons, the financial aspect is also important, but it's also interesting. So that's why I said, okay, probably IT is a good choice. However, that's a good question, because to be honest, in the professional career, I always slightly regret that I didn't do astronomy, because I'm considering, should I shift the career to the switch. So, okay, yeah, that's it. Sorry, it's too long, so that's enough of me. I think that we can stop unless any questions. So tell me if it's too fast or too slow. So then we use the same timeline, but more, let's say, even high level. And this is the story starts. Again, some of you know the story, but you can help me, obviously. And you're more than welcome to come. So the story starts back in 1958, if I remember correctly. There was a large antenna built by Labs. It looks like this. So you see the people there. So, and this is especially the horn antenna. And the horn antenna for the microwaves. And the close analogous is this musical instruments. And this is for the sound waves, but the principle is the same. It just collects the waves and magnifies this thing. As you know that better. I don't need to explain you that, because the telescope works exactly the same. So, and the idea in Bell Labs, what they wanted to do, they wanted to use this antenna to send the signals and the phone calls from one coast to 2 years to another coast from years, because the communication was booming that days. After a few years of trials, that was not successful, and they decided to donate or to give this antenna to scientific research. And that's when commercial part stopped and the scientific part started. And some people decided to repurpose the antenna to analyze radio signals from the sky, exactly microwave radiation. So, what happened? These two gentlemen, Robert Wilson and Owen Pensalas, they discovered that there are three things. That the telescope is very sensitive, because this antenna became a radio telescope once it's converted from the commercial one to the scientific one. The signal is very weak, actually, this is another discovery, and there is a noise in the signal. So you see there are good news, this is very sensitive, but there are bad news, there's a weak signal, plus there is a noise in the signal. So it's like one good thing, two bad things. So they decided to see what they can do with this, because they wanted to study the galaxies and also to remote objects with this radio telescope, but they got constant noise, so they want to understand what is the reasons. So they tried one by one to eliminate the reason. This was located not far from the New York City, and they also tried to understand if it's noise from the city. So they positioned the antenna in different directions to eliminate that, but it was not there. Also, noise from the heat was excluded, was not there. military. There was a military station with a radar very close to the place, and they called the military people and asked him if the radar is operational. And the soldier said, or the lieutenant said, no, it's not. So they said, probably not. The silent planets, they also tried that. A reason, but it didn't prove the value that it is that. And then faulty wires a telescope part. For that, they spent quite some time, if I remember this story correctly. They inspected all the radio tracks, etc. So that was not the reason. Well, finally, they found the reason, actually. So, at least they thought that. They checked the surface and found these pigons there, which produced this white electric material, because the antenna was very nice to nest them. And they decided to take the birds and clean up the telescope, which they did actually. The problem with the pigons, they tried to move them in the kind of carriage away from the telescope, but they did it and they always returned because they move it not far away from the telescope. I think you need to move the pigons very, very far away, like hundreds of thousands of miles away, so they could not return, but they don't do that. They remove them only maybe to the 30, 50 miles, which is very short for the birds. And they found the antenna back. And yeah, so well, unfortunately, what happened is that they tried many times, but then they tried. Okay, maybe we need to just kill the birds, and then maybe it will end. So let's leave them here, because there was another part of the story in the Princeton University. So this gentleman led a research group, and they decided to design an experiment. So, and the experiment was to check the theory prediction, because the Big Bang theory, well, the theory, as you know, was invented here in Ireland, that the burst of radiation should be visible today from that days, and that there should be a microwave background, as you know. Actually, they were doing this research preparation. Well, actually, they were doing the classical design experiment focused on the instrumentation and observation plans. Eventually, what happened is that Arno, from the first team, he mentioned that they are struggling with the pigons and with the birds and with the noise to the person that was reading the paper by members of his team. And after the conversation, the historical phone happened when Arno called Princeton University, called Dickey actually. And when it happened, then Dickey said, oh yeah, somebody just was in front of us, because he understood that actually that was a discovery. So, two scientific papers published immediately there, both by Dickey team and by Arno and Wilson team, and they won a Nobel Prize in Physics, as you probably know, and that started the new era of golden age of cosmology. Well, one of the reasons, or two reasons, why I decided to present this small and inspiring story for the colleagues at my work, because first, their persistence, the persistence to remove the noise and to improve the observations are very remarkable. Because if they will give up, or if they will try to continue research with the noise, then maybe it will be very long until this discovery, right? So, and then one of the inspiring things is that they try to look on the data, try to look on their observations and try to improve it. This is number one. And I think this is applicable for any other fields. Number two, they talk to the people. So they constantly shared, they made the connections, and without that, it won't be possible that somebody heard about this research and that happened. So that's why I decided to share this story with colleagues and also with you. Yeah, probably all of you know this story, I don't know. Was it new for someone? Oh yeah, really? Oh, okay. Very nice to hear. Anyway, maybe we can discuss this. Any questions, any reflections on this story?
So the type of antenna I always found is very remarkable, how it is shaped, like a big ear. And it is not used anymore, is it?
No, I think it's a museum type. Like there was a table there. This is what I heard. There's a table of this historical place, but I think it still existed today. So some people can visit it.
It still exists. So the original ones still exist, but the type of antenna has never been reproduced to be used. Why not? I can imagine it was designed for radio communication. We found better methods or better antennas or shapes. Maybe somebody knows.
Yeah, parabolic antennas are easier to build and are much more efficient than a horn antenna. A horn antenna has this capture capture surface is much lower than with the same amount of metal in a parabola.
So they were effectively replaced by parabolas.
I think because of efficiency. Because I think, thanks for this answer, because I'm just thinking based on your answer that we have all examples in our present life, or many examples they based on parabola or this spherical, because satellite dishes, then radio wave dishes for the microwave stations for the satellite communication, that transmit the signal from one tower to another tower. Yes. You might notice that they also round at this type.
Could it perhaps have to do something with the detector use? It has to be close to the equipment to read it out or something?
No, in this configuration, the detector is near the box, near the house, the housing.
That's what I mean. Yes, if you put it on a
parabola, you have it
that perhaps they needed to be close to the detector with all equipment.
Yeah, because the parabolas, the detector was too large, it would cover the parabola, and if you would go larger, it would collapse. That's possible, yeah. I find it a pity that they disappeared, because I like the shape of this antenna very much. Imagine this weekend...
You can blow at the other end.
Yeah. That's what you...
And send signals.
We go to Effelsberg, right? And Effelsberg is one of the largest dishes in the world, at least single dishes, I think, movable. It's 100 meters, I'm not sure. Imagine the 100 meters dish to be replaced by a sizable horn like that also. That would be fantastic. Yes.
And a recent, I don't know if you know Scott Manley on YouTube. That's a guy who is talking about space and everything that happens, and he spoke also about this antenna, and that at this moment it's a ruin, it's going to waste, and he's trying to get it revived, that they will restore the original antenna. Because it exists, and on YouTube I will share the link. There is also some images from this original antenna.
Okay. Or it could just be a receiver, it's just way too heavy to put on a stalk in front of a parabolic dish.
Yeah.
It's a complicated design to move all these parts, while with the parabola you have a German equator mount, which is a bit bigger than our mounts, but
probably I
think
think
it's the same.
I think
this is an azimut alt.
Altism, yeah, because
this is an azimut alt and
one.
Yes, this is an azimut alt.
This is this one and this is this one.
Yeah.
But this is not scale up, because this is maybe, I don't know, 20 meters, but if you want to have 100 meters, then this is very difficult to make and this is very difficult to make. So the scale up is not possible.
Going to look it up.
Huh?
I'm going to try to find out.
If it's difficult.
But
if it's difficult or not. Well, are you going to try to find out?
Because I find it interesting when you put that shape in.
It's a shape, yeah.
But I know that even it's difficult construction-wise because Arecibo collapsed, and Arecibo in Puerto Rico, the large one, and also the Green Bank telescope. So there was an antenna, classical antenna dish, it was also collapsed. And the reason is also it just fell down. So there was nothing like, no strong wind, nothing like that, it just fell down. No one got hurt, but there was a large parabola dish just collapsed.
But it was like that in the 50s. When was this built?
50, I think 50 something.
I know also from military data, things like that, they were severely constrained more by the receivers, senders and receivers use than by the antennas themselves. So the antennas followed what was possible with receivers, like weight and size.
Yeah.
This is, in fact, this is a waveguide antenna.
Yeah, and that was
And
the
a parabola is not a waveguide. The waveguide is eventually in the receiver, in the converter, because signal, the high frequencies are converted here and are transported to the equipment, the receiving equipment. But this is a waveguide antenna, and this is an whole other concept than a parabola.
So why is that? So because the parabola is reflecting the radio signals into the center.
It's like a mirror. It's
And
like a
isn't
dot
this capturing the same and guiding it to a central point? It's also reflecting. It's also
It's
metal.
not reflecting. It is.
But on the
It is
inside.
the guiding. It's like Michael explained with the horns. Horns are also wave-guided tools.
Yeah.
The sound is amplified because it is the pressure of the sound differs, but amplifies because it is expanding, and it's the same. It's the same with waveguides.
It's
In
different
microwave,
kind.
it's
contact.
in microwave.
So the principle is totally different.
The principle is totally different. What you with the parabola, you have reflective surface, and it's reflecting to this brandpunt, is focus point, where you put the receiving, the little receiving antenna. The real antenna is in fact in the top of a parabola.
And this is completely antenna.
This is a complete antenna. So the waves come in and are guided through the tube to the receiver, which is at the little house.
Yeah, thank you. That's indeed very good. But this is very similar, but for sound waves.
It's the same.
Let's say
If you the first recorder from Edison was of that type. So here you have the sound is produced by the platter, but in the other direction, when you speak into the horn, it is also amplified, and you can make a needle move
recording
on a cylinder, and you can record.
Record.
That was the first recording from Edison.
Very interesting.
So,
Yeah.
you think perhaps that then the size and geometry of the wall part may be tuned to the specific frequencies.
It is possible, but you have the harmonics who pass through also.
Because this was not designed to capture background radiation. I mean, now we know that the background radiation is 21 centimeters.
21 centimeters.
Wave.
Yes.
Is that the
hydrogen?
Yeah, that's the amplitude. No, it's the frequency.
The frequency.
So we have a wave like this.
Yes.
And this one, this antenna, was very good at capturing it, or not? Was it coincidence? That was coincidence, then I guess.
But I think the frequencies that they wanted to operate, this was like comparable. This
microwaves.
The microwaves, because they wanted to send these phone calls.
Centimeter waves.
Centimeter waves, because they wanted to use this for these phone calls from one coast to another coast.
Across oceans?
No, across the US, from eastern to western, across the US, because they wanted to have the. This is what I remember. Some, how to say, in the stratosphere, like a balloon, which will reflect. So this antenna will send the signal, and another antenna will get the signal using the balloon. Actually, the balloon which is high enough. So
Okay.
If I remember correctly.
Yeah, you don't have a direct line and with
No direct line, because they need to have a reflection. So they wanted to send the signal, then receive the signal, then send the signal again, and receive the signal, and then across the US, because US is a very wide country.
But it never worked.
There was some I think at some point, I think there was I don't remember, but there was another technology which proved to be way better. And they just decided that, okay, we don't need for the commercial use. I don't know, maybe it worked, but maybe not, but they decided to use another technology to transmit the phone calls. I don't remember which they decided to use for the phone calls. Could be cables, could be...
So how is background radiation 21 centimeters, how is that captured today? Is that something
with
that they go
21 centimeters? Isn't that hydrogen radiation?
Yeah.
I don't know if background, that's black body radiation.
That's black body radiation.
It's something different.
Is it different?
21 centimeter is the flip of proton spin and electron spin. So that is 21. And background radiation, cosmic background, is a black body.
Yes, black body.
Black body from 3000 and Kelvin.
Yes.
When ionization stopped.
I think so. Yeah, I don't remember, but yeah, the frequency...
But now I'm confused. So
it's a black body. It's all kinds of frequencies. Black body background.
So this didn't discover background radiation.
That was cosmic microwave background.
And that's not 21 centimeters.
No, 21 is a hydrogen flipping from proton spin and electron spin up and down.
But isn't the background radiation the result of the hydrogen radiation that has been redshifted?
No, it's because of stopping the ionization. It's called reionization, but it is wrong. It is deionization, because before, actually, the cosmic microwave background originated 380,000 years after the Big Bang. After the Big Bang, everything was ionized. After nucleation was formed, nucleons were formed, nuclei were formed, and atoms were formed only 380,000 years later after Big Bang. That is, you had free nuclei and free electrons. Universe expanded, everything cooled down. It cooled down to about 3000 and some Kelvin. At that temperature, atoms form. We can do the reverse. We have atoms, we heat it up to 3000, and it starts to be a plasma, like the sun. The sun is a plasma. The sun is not opaque. Our gas, hydrogen gas, is opaque. The sun is not opaque. So the universe at 380,000 years was not opaque like the sun is today. So you couldn't see through. It cooled down. Plasma was reverted to atomic gas, which is opaque. So only at that time, photons could travel through the gas and not the plasma anymore, because photons get
trapped, in plasma. Stopped or blocked. Yeah.
It stopped. They get. There is a word I don't get.
Yeah.
Photons get bounced off all the time.
What is it?
Scattered. They get scattered. Photons get scattered. There was no meaningful signal going out. When it reverts to a gas, photons pass straight through. Like today, photons, we can see each other pass through a normal atomic gas. So at that time, that cosmic microwave background radiation, which was radiation at a black body temperature of 3000 Kelvin, was released into the universe. In the meantime, the universe expanded. Today, the expansion resulted in the cooling down of the radiation to 3 Kelvin, 2.7 Kelvin,
Yes.
because of the expansion. So you have that wave of the photon, universe expands along with it, it stretches the wave of the photon. Today it cooled down to 3 Kelvin. They received the 3 Kelvin black body radiation, which is its frequencies all over the place, so you have to check two frequencies, and it can reconstruct, I think, the whole black body radiation curve, because it's only depending on two parameters. One is the temperature, and then some.
But also that's very clear, because it was light, but because of the increasing of the
Became microwave.
it became microwave.
From the frequency, but what is the frequencies of the sun? We know yellow, which is about 500 nanometers.
Yes,
It went all stretched up to centimeters.
yes. And this is microwave.
This is the proof that Big Bang happened, because they could prove this light was redshifted from plasma to gas to today, plasma radiation to today's gas of black body of 3 Kelvin. Actually, there was a group before the group of Dike and no, the other one. Yeah, Dike and it was Peebles, Jim Peebles. Dike and Peebles.
Peebles, yes.
They
Peebles, yeah.
They calculated, and they used the very famous article of Gamow, this alpha, beta, Gamow, alpha and Gamow.
Yeah, Gamow. Yeah.
They calculated nucleosynthesis few minutes after Big Bang. So they calculate what kind of abundances of the elements were to be in the early universe. And they said, if that happens, the hot plasma, which was forming at the time, must cool down to form atoms. And they said, oh, but we should be able to see that radiation. That was forgotten, that was in the war or something, that was quite forgotten. And then Penzias discovered it, while Peebles and Dike were reanimating the work of Gamow. And Gamow was not pleased at all that these fellows got the Nobel Prize and not Gamow was not included. And there was a very famous article, Alpha and Gamow, that was like alpha and beta, and they called alpha and gamma, which were working together, and they called Hans Bethe, which had nothing to do with the research, but Gamow was a joker, and he said, hey, Hans Bethe, can I add your name to our article about nucleosynthesis? Then we have alpha, beta, gamma, alpha, beta, gamma, which is a very famous and practical joke of and Bethe was actually the famous fellow that elaborated nucleosynthesis or nuclear fusion in stars. Hans Bethe was the first one to elaborate what reactions were happening, creating energy in stars.
And Gamow, I think he's
a Russian.
He's Russian, yes.
But
he lived in the United States, I think.
Yeah, he tried to escape from Russia at the time in a small canoe with his wife and a box of chocolate. But the security fellows got him, and they asked him, "You trying to defect?" "Oh no," he said, "we were just having a fun day out on the lake or in the sea with a small boat and a box of chocolate."
Okay. Yes, thank you.